We are balancing stock across a global network. If you keep too much stock upstream, you tie up working capital and increase the risk of obsolescence. If you keep too little stock downstream, you create stockouts. That leads to lost sales and dissatisfied customers, which can damage long-term demand. Multi-echelon inventory is hard because uncertainty and coordination interact. Risk pooling means that centralized inventory can buffer demand variability more efficiently than fully decentralized inventory. At the same time, uncoordinated ordering causes the bullwhip effect, where variability amplifies as you move upstream. That is why coordinated policies matter. This diagram shows the network structure behind the problem. Products flow downstream from upstream facilities, and information flows upstream as orders and forecasts. When you choose inventory targets, you must consider lead times, capacity limits, and where uncertainty should be buffered. The structure determines where inventory is most valuable. This chapter uses a tiered approach. Tier 1 uses stochastic programming to create a rigorous baseline under demand uncertainty. Tier 2 uses a scalable echelon-by-echelon heuristic. Tier 3 and Tier 4 introduce advanced search and demand learning, and the later tiers extend to digital twins, human oversight, ethics, and quantum-inspired computation. Tier 1 treats demand as uncertain and represents it through scenarios. First, you decide base stock levels before demand is known. Then, after demand is realized in a scenario, you compute the costs that result, such as holding cost for leftover inventory and penalty cost for backorders. The objective is to minimize expected cost across scenarios. This slide defines the core sets and indices. We index locations in the network, we index time periods, and we index demand scenarios. Each scenario has a probability, and that probability weights how much its outcomes contribute to expected cost. This is the foundation for making decisions that perform well across uncertainty. These parameters translate operations into cost. Holding cost captures the cost of carrying inventory over time at each location. Backorder penalty captures the business pain of not meeting demand at customer-facing points. Transportation costs and lead times connect echelons and determine how quickly inventory can move. The decision variables include a first-stage base stock level at each location and second-stage operational quantities such as inventory on hand, backorders, and shipments. Operationally, base stock is your target inventory position. The second-stage variables capture what actually happens under each scenario and each time period. The objective is to minimize expected cost. In each scenario, you pay holding cost for inventory carried and penalty cost for backorders. A good policy balances the cost of safety stock against the risk and penalty of stockouts. By weighting scenarios with their probabilities, you optimize for average performance under uncertainty. Inventory balance is the accounting backbone of the model. It says that your net inventory position at the end of a period equals the previous position plus inbound flows minus outbound flows. Lead times matter because inbound shipments arrive after a delay. This constraint prevents impossible flows and ensures the model respects the physical timing of replenishment. Demand fulfillment enforces that retail-level demand must be covered by outgoing shipments. When demand is not met, it appears as backorders. This captures the service-level side of the problem. Without this constraint, the model could pretend demand disappeared, which would hide the true cost of stockouts. The order up to logic expresses a base stock policy. Each period, you order so that your inventory position returns to the base stock level. This is a common control rule in practice. The model either enforces it explicitly or emerges toward it by minimizing the combined holding and backorder costs. Non-negativity ensures all quantities stay physically meaningful. Base stock, inventory, backorders, and shipments cannot be negative. These basic domain rules are crucial for keeping the solution operationally feasible and interpretable for planners. Now, we ground the model with a simple two-echelon example. One warehouse supplying one retailer. We assume holding cost of $1 per unit per period at the warehouse and $2 per unit per period at the retailer, plus a backorder penalty of $10 per unit. Lead time is 1 period, and demand has 2 scenarios with equal probability. Consider a policy where the retailer targets 15 units and the warehouse targets 25 units. Under low demand, the retailer ends with 5 units and pays holding cost. Under high demand, the retailer faces a shortfall of 5 units and pays backorder cost. With equal probabilities, the expected cost for this policy is $40. Tier 2 introduces a pragmatic heuristic. Solving the full scenario model across many locations can become computationally expensive. Sequential echelon optimization works by solving downstream first, then propagating the implied demand upstream. This creates a scalable approximation that is widely used in practice. The heuristic has a clear sequence. First, optimize each retail store based on its own demand and lead time. Then treat the resulting order streams as demand for the distribution center. Optimize the distribution center next, and repeat upstream until the central warehouse policy is determined. This diagram illustrates the downstream to upstream logic. Each echelon is optimized using the demand signal coming from its children. In practice, this is where the bullwhip effect can emerge because upstream demand is shaped by ordering policies and batching behavior rather than pure end customer demand. A common way to build the heuristic is through safety stock and reorder points. Safety stock is driven by a target service level and the variability of demand during lead time. Reorder point is the expected demand during lead time plus the safety stock. This provides a simple and interpretable control policy. This slide shows a compact Python implementation of the sequential heuristic. It processes locations from downstream to upstream. When a node has children, it aggregates their demand streams to estimate its own demand. Then it computes safety stock and reorder points using a service level z-score and the lead time demand variability. In this part, you can see the implementation details in action. Key functions in this chunk include calculate policy and sequential echelon optimization. You will notice logic related to demand. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, you can see the implementation details in action. You will notice logic related to demand. As you read it, follow the data flow from inputs to outputs, and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. This slide focuses on Tier 2. Example output from the worked numbers. Key points shown are SPITE for retail. A. Safety stock is about 11.67. Reorder point is about 51.67. For retail B, safety stock is about 18.67. Reorder point is about 78.67. Distribution center demand becomes mean 50 and standard deviation about 9.43. For the distribution center, safety stock is about 34.78. Reorder point is about 284.78. Operationally, use these points as a checklist. Confirm the definitions match your data, confirm constraints reflect real limits, and confirm reported results are consistent with the scenario and the objective. A key design choice is how to encode a policy. In this context, one moth is a vector of reorder points or base stock levels for every location. Fitness evaluation runs a simulation over demand scenarios and measures total holding and backorder outcomes. The better the cost, the stronger the flame becomes. The spiral update step is designed to balance exploration and exploitation. At first, moths can move far from a flame, exploring alternatives. As iterations progress, distances shrink, and the algorithm exploits the region around the best-known flames. This supports convergence toward high-quality inventory policies. This slide focuses on Tier 3, moth position and fitness. Key points shown are: a single moth encodes reorder points or base stock levels for every location. Fitness evaluation runs a supply chain simulation and sums holding and backorder outcomes. Constraints are enforced by bounds and repair rules during updates. Operationally, use these points as a checklist. Confirm the definitions match your data, confirm constraints reflect real limits, and confirm reported results are consistent with the scenario and the objective. This slide focuses on Tier 3, Spiral Update Intuition. Key points shown are: each update moves a moth along a spiral toward a selected flame. Early iterations allow wide exploration around flames. Later iterations shrink distances to exploit the best regions found. Operationally, use these points as a checklist. Confirm the definitions match your data. Confirm constraints reflect real limits. And confirm reported results are consistent with the scenario and the objective. This diagram shows the architecture of the variational autoencoder used to learn demand patterns. The important operational idea is that demand scenarios can be generated by sampling in the latent space. That gives you richer and more realistic stress tests for inventory policies. In practice, the variational autoencoder helps in two ways. First, it can generate synthetic demand scenarios that reflect realistic correlations. Second, it can compress the network state into a manageable signal for a learning agent. This makes advanced learning approaches more feasible in large networks. Tier 5 moves to a digital twin. This is a high-fidelity simulation that is continuously updated with operational data. It supports what-if analysis and allows planners to test policies before deploying them. It also provides a safe environment to embed optimization and learning methods. This slide outlines the architecture of the digital twin. It connects physical assets and enterprise systems to a modeling and simulation layer. On top, analytics and dashboards allow planners to explore scenarios and compare policies. This creates a feedback loop between real operations and model-driven decision-making. A concrete scenario is a supplier disruption in Vietnam lasting 4 weeks. The twin freezes that supply lane and simulates the network forward. It predicts where stockouts begin and how they cascade across echelons. Planners can then test mitigations such as alternate suppliers, expediting, and inventory rebalancing. Tier 7 describes the Centaur planner, a partnership between human expertise and artificial intelligence. Artificial intelligence analyzes data and proposes policy changes with explanations. Human planners apply context, relationships, and strategic intent, and the system learns from overrides and outcomes. This slide focuses on Tier 5. Concrete example: supplier disruption. Key points shown are: scenario: a major supplier in Vietnam shuts down for 4 weeks. The twin projects when stockouts will begin, first at the central warehouse, then at distribution centers, then at retail stores. Planners test mitigations such as alternate sourcing, expediting, and inventory rebalancing. Operationally, use these points as a checklist. Confirm the definitions match your data. Confirm constraints reflect real limits, and confirm reported results are consistent with the scenario and the objective. A typical example is an explainable suggestion to increase safety stock for a specific item at a distribution center by 30%. The system justifies it by showing demand variability increasing by 50% and lead time reliability declining. A human planner can override if near-term business context changes the risk picture. Tier 8 introduces value alignment and ethics. Pure cost optimization can unintentionally reduce service in lower-income or hard-to-serve regions. A value-aligned approach embeds fairness constraints. This ensures that essential items maintain acceptable service levels across all groups, not only where it is cheapest. This slide focuses on Tier 7. Concrete example: explainable recommendation. Key points shown are: example: increase safety stock for a specific item at a distribution center by 30%. The explanation cites demand variability increasing by 50% and lead time becoming less reliable. A human planner may override if a new supplier is coming online soon, or a campaign is upcoming. Operationally, use these points as a checklist. Confirm the definitions match your data. Confirm constraints reflect real limits, and confirm reported results are consistent with the scenario and the objective. This diagram shows the ethical governance layer wrapping the optimization engine. The governance layer monitors and enforces fairness rules and service level commitments. It ensures the system does not sacrifice essential service in pursuit of marginal cost savings. A useful way to interpret the fairness rule is through a clear minimum service target for essential items. For example, you might require at least 95% service for essentials across all groups. The optimizer can still reduce cost, but it cannot violate that minimum without incurring a large penalty. Tier 9 looks toward quantum annealing. Multi-echelon inventory decisions become combinatorial as the number of locations and items grows. Quantum annealing requires expressing the problem as a quadratic, unconstrained binary optimization model. The practical step is discretizing policy levels and mapping them into binary choices with penalties. This slide focuses on Tier 8, interpreting the fairness rule. Key points shown are: a fairness penalty becomes very large if service level for a group falls below a threshold. Example threshold: 95% for essential items. A large weight forces the optimizer to prioritize fairness over marginal profit gains. Operationally, use these points as a checklist. Confirm the definitions match your data, confirm constraints reflect real limits, and confirm reported results are consistent with the scenario and the objective. This figure illustrates mapping a network policy into the connectivity constraints of an annealer. The idea is to encode each discrete inventory choice as a binary variable and let the annealer explore the energy landscape. The result is a candidate low-cost policy under the encoded objective and penalties. Discretization and constraints are central. For each location, you allow a small set of stock levels and use one binary variable per level. Then you add a penalty that enforces exactly one level is selected. Costs and multi-echelon interactions are encoded as weighted terms, so the chosen combination balances cost, risk, and coordination. This slide focuses on Tier 9, quadratic unconstrained binary optimization, mapping to qubits. Key points shown are: mapping the multi-echelon inventory problem onto a quantum annealer via a quadratic unconstrained binary optimization formulation. Operationally, use these points as a checklist. Confirm the definitions match your data, confirm constraints reflect real limits, and confirm reported results are consistent with the scenario and the objective. These questions extend to digital twin mitigations, Centaur decision-making under geopolitical risk, and ethical governance justification. They also ask you to reason about quantum mapping, including how many binary variables are required to represent discrete inventory choices, and how to enforce one-of-k selection. The key takeaway is that multi-echelon inventory requires coordinated decisions across locations, time delays, and uncertainty. A rigorous baseline helps you understand the true trade-offs. Scalable heuristics help you deploy, and advanced tools like simulation, learning, and governance help you operate reliably in complex real-world conditions. This slide continues the structured explanation of multi-echelon inventory planning. Focus on the operational meaning of what is shown and how it affects total cost, service level, and coordination across echelons under uncertainty. This slide continues the structured explanation of multi-echelon inventory planning. Focus on the operational meaning of what is shown and how it affects total cost, service level, and coordination across echelons under uncertainty.